How many receivers are there on Earth?
There are thousands and thousands and thousands of sensors all over the planet. Earthquake happens and thousands of recordings. How do you look at thousands of recordings, like really carefully?
You were talking about kind of where it used to be, squiggles on a piece of paper.
Right, it was drums that turn really slowly by a machine, and there's a pen. And voltage is like wiggling the pen when some seismometer. So we have a big data, it's a good problem, where we can't actually look at all the data anymore because there are literally millions of recordings. Where in the old days, an earthquake happened, if you had 30 recordings when I was a grad student, that was a good day. Now, if you had 30 recordings on an earthquake, you'd be like, next. We want thousands of recordings. The procedures are automated. It's a challenge. AI and machine learning are getting into the game. And how do you know that they're learning the correct thing? How do we look at the information when there's too much for any human to look at?
Welcome to SCL Podcast, filmed in the MD Acoustics Anechoic Chamber in beautiful Gilbert, Arizona. Today, we are joined by ASU professor Dr. Ed Garnero, a geophysicist who is now applying his decades of research to the art of Lutherie, the art of crafting stringed instruments. Each episode, we bring you compelling conversations, practical advice, and illuminating stories from the minds of industry leaders, educators, innovators, and visionaries who are shaping the world one idea at a time.
Got Jocko here with us. Now we have Fleet with us. Love it. Hey everyone, welcome to SCL Podcast. My name is Jordan Trubakoff. This here is Robert Pearson, and we're joined today with Mr. Edward Garnero. Edward is a professor at ASU. He originally got his PhD in geophysics at Caltech. Thousands of citations. How many publications? Well over 120? Do you keep count anymore?
I don't really.
You don't have enough fingers. Ed, how long have you been at ASU?
Almost 27 years.
27 years. And during that time, you got voted favorite professor a few times.
Yeah.
Is that through the students?
Yeah, there's a student nomination thing. There's a teacher of the year nomination thing that comes from another organization. Just, there's so many gifted professors there. So I'm surprised anyone ever, like I got through even to be a runner-up.
The geophysics that you do, right? You're studying the interior of celestial bodies, including Earth.
Yeah.
And when we were talking a little bit about it before this, you were talking about kind of where it used to be with reams of paper and squiggles on a piece of paper, and now it's become. How many receivers are there on Earth?
Yeah, you're right. It was drums that turn really slowly by a machine, and there's a pen. And voltage is like wiggling the pen when some seismometer that's in a basement is like, I'm shaking. And, hundreds of them. And now there are thousands and thousands and thousands of sensors all over the planet. And the data are publicly available if you have an internet connection. And earthquake happens and thousands of recordings you can look. And how do you look at thousands and thousands of recordings, like really carefully? So we have a big data, it's a good problem, where we can't actually look at all the data anymore because there are literally millions of recordings of earthquakes. Where in the old days, an earthquake happened, if you had 30 recordings when I was a grad student, that was a good day. Like, I got 30 recordings for this Fiji earthquake. Oh my God, it's amazing. And now if you had 30 recordings on an earthquake, you'd be like, next.
Yeah. It's just, it's a slow Tuesday.
Exactly. We want thousands of recordings and the procedures are automated and it's a challenge. Like, how do you know that your automation and now AI and machine learning are getting into the game? And how do you know that they're learning the correct thing? And so our community is starting to think about that. How do we look at the information when there's too much for any human to look at.
Right. Yeah, AI. I haven't even thought about using that.
But of course, it's coming in.
Yeah.
It goes in everywhere.
Yeah, it's like I'm so impressed with what smartphone companies have done.
Mm.
I pull out my phone and Apple figured it out. I'm speaking and the words are showing up on my screen. So, and it really is just time amplitude information, like seismic information, right?
Yeah.
And okay, there's different frequencies or pitches, high frequencies, low frequencies, treble and bass in what I say. How's that recognition happening? That's AI. There's a vocabulary that it learns words. And the more that we do it, the better that it gets.
So something that some people might not know is you did a TED Talk. We talked about it a little bit ago. Something I found very fascinating in that TED Talk was you actually explained that you could have an earthquake all the way over in California, right? And still read it all the way on the other side of the country, possibly the other side of the world, right? That's insane to me. That wave has not died down by the time it reaches that far, right?
Yes. Yeah, okay. You could think of something locally. If you roll over in bed, you might wake up your wife because the bed's shaking because you shook. But somebody in the kitchen is not going to feel it. But if you are in a larger space and you jump up and down, someone might feel it. Like you can maybe feel a neighbor in the next suite if they're hammering something. So sounds get absorbed, motions get absorbed, and they don't last very long. But the bigger the motion, the more you can see it, right? Like you throw a rock in a lake, you could just watch those waves travel the surface. Well, earthquakes are a large amount of energy. It's slipping on a plane, and those areas where that slippage occurs can be miles or hundreds of miles, or even for the greatest earthquakes, magnitude 9s and above, it could be, like 1,500 kilometers or 800 miles of a fault zone that breaks. Something that big, that energy propagates through the whole planet. It travels through the planet, ripples along the surface like an ocean wave. And so anything about magnitude 5 or larger can be felt by our sensitive recording devices anywhere on the planet.
Interesting.
So, and there are dozens of earthquakes every day. And so one thing we don't think about is that those vibrations from dozens of earthquakes, there are many earthquakes that are large enough to see around the planet. There are thousands and thousands of earthquakes every day. Some of them are tiny, tiny, tiny. Nobody knows because there's not even a sensor near it. But anywhere on the planet, the earth is always vibrating from earthquakes.
Yeah.
Always. And another interesting thing, you guys being an acoustics firm, there's like sources of energy, right? I break seismology down into 3 things. Sources of energy. That's in my field, it's like the earthquake. In your field, it might be a device where you're sending waves and looking at reflections. There's the traveling of the energy.
Sure.
And so that's what we're talking about. Okay, the earthquake happens, it travels through the earth, and it gets recorded. Then there's the response of the medium. So the earth is actually a shape, right?
Yeah.
You can think of a pipe organ. The pipes are different diameters, or an electric bass guitar has a certain shape to it and its own natural frequencies. The earth is actually also a shape. It's a sphere that's, 13,000 kilometers across, that if you like tapped it with a hammer from space, you would hear a ringing. That fundamental vibration in earth takes about an hour to vibrate there and back. Like, talk about low frequency.
Yeah, wow.
Yeah, it's so you can't hear it obviously because it's something that goes distorted back to its original shape. One cycle takes almost an hour. We call it free oscillation. Like you've seen drops of water in the space shuttle where there's like bloop, bloop.
Right.
Yeah.
And the earth also has shearing motions. Those don't take it quite as long. So an earthquake that's big will ding the earth that way. So those pitches are happening in the overtones. It's really interesting.
Okay.
So it's such a cross section between music and instruments and seismology.
So the classic model of the earth, right? I'm thinking it's an onion, right?
Yep.
the crust,
Yeah.
mantle, all that. Different densities,
Yep.
viscosities.
Yeah.
It's a very complex mechanism.
Yeah.
How could you possibly comb through all of those different mediums with different pressures and see an earthquake in California, pick it up in France, and how can you pull data with such a complex moving mechanism to have them speak to one another? Or is that's almost the whole premise, is having those 2 meters, because you can use the differences between the two of them to kind of map the inside?
Yeah, it's a great question. It's not as complicated as
says the man with the PhD.
Yeah,
Yes.
it's as complicated as we explain it. And the curse of knowledge, sometimes we forget what others don't know, but it's not that complicated. Like, if I'm talking now, you're actually hearing me more.
Right.
Yeah.
Fair enough.
Sorry,
Okay.
you're hearing me louder than he is. You're hearing me sooner than he is. But
Sure.
our ears just aren't that sensitive.
Right.
But if we had a seismometer at the two of you, you would see my signal arrive first. You would see it arrive
Uh-huh.
second.
Right.
Maybe a little diminished in amplitude. And so if we had enough sensors around the room, you could figure out where I spoke. Because it had to originate by triangulation.
Right.
Yep.
Right.
Yeah.
Right.
We do the same thing in acoustics.
Yeah,
Right.
exactly. So the you brought up a good point. Okay, the Earth is layered. It's getting denser as you go in, and all these layers. And so
Right.
sometimes there's some things in the way. The core gets in the way. It's like an eclipse, The moon got in the way of the sun. So same thing happens with the core.
Okay.
But things will diffract around it, just like the way light can diffract around
Right.
objects. But ignoring that complication,
Yeah. Don't worry about that, little guy. Don't. Yeah.
why did I even say it? So you could sort of, and that the speeds of the waves are changing with depth in the planet.
So you're making it more complicated.
Right, I'm making it more complicated than air in this room. The speeds change maybe near the light bulbs.
Right.
Because it's hotter, so it slows down a little bit. But we figure that out slowly but surely because, okay, the close by sensors, it takes so long, so you can figure out the speed of the wave to get there.
Right.
If you guys both say, hey, we're going to your house because you're having a party. And I'm like, okay, what time are you guys going to leave? And I'm leaving at 10 o'clock sharp. And then you get there first. I could assume you live closer.
Fair enough.
And you get there 15 minutes later, I could assume that you live further away. But then you're like, no, I got stuck in a traffic jam. So my speed was delayed, right? So the speeds of the waves are at play. But an earthquake happens in California or here in Arizona, and in Paris, a seismometer picks it up. And then in Kyrgyzstan, there's another seismometer. And in Maine, in the US, there's another seismometer. You could start to figure out where things occurred. And now this is all goes into computer algorithms now, because we roughly know the speeds of the planet with depth to do that triangulation and backtrack out where the thing happened. So we have that. So it's not like I go with a ruler and all these graph papers and I'm like, this one's in Fiji. Yay!
Yeah.
No, it's like that's all automatically done.
Yeah.
And then where it gets interesting is, okay, that earthquake in Fiji happened and we recorded it here in Arizona, but the wave shows up 5 seconds late. We're like, we know enough about where this earthquake is, and it doesn't show up 5 seconds late to Berkeley. You're like, okay, something's up.
Oh, right.
So, and then you use those time delays. Like, you showed up a little late. I'm like, you stopped at the convenience store, didn't
Right.
you?
Yeah.
You went to Dutch Bros. I know it.
And you didn't ask me if I wanted it.
Yeah, and you're holding one, so I know that.
Right.
So he's 10 minutes late. So you use those travel time,
What a rude earthquake.
Yeah.
earthquake anomalies to say something happened along this path between Fiji and Arizona.
Yeah.
And oh my gosh, if you do that with enough earthquakes crisscrossing the medium, then you're getting into like what we all know from medical tomography and ultrasound, like there's something in there
Right.
that
Yeah.
made the wave more sluggish. And so now we know about these massive anomalies in the planet, these blobs and things like that, that we're trying to sharpen the focus on those, using those really subtle, sometimes it's just a couple seconds, delays or advances of seismic waves that are crisscrossing the planetary interior. That was a mouthful, I know.
No, but
you understand it, right?
Yeah, absolutely,
yeah.
absolutely. It's one of those things where it's like it almost creates more questions than answers. But the answers that I'm getting from it, I can go, okay, I can apply this to others, to my life.
Yeah.
You know, so it's just such a fascinating field.
Now, there's one question I do have, because you are part of the science of Earth and space exploration. Are you an astronaut?
Yeah.
And do we have?
How do we get in on this?
Do we have things on the moon? Does the moon have earthquakes?
Okay, let's start with, am I an astronaut? I would say I'm an explorer.
Ooh.
Okay.
Yeah, and when we were the Department of Geological Sciences. We grabbed all the astrophysicists from the Department of Physics, brought them over. We hired some engineers, because if you're going to go to space, you want devices people. And it was kind of a shift from geological sciences, Earth and space exploration. And I'm like, does that make me an explorer? So it's like, is this an existential crisis, or is this exciting? So I'm like, wow, I'm an explorer. Wow, because I'm curious, and I'm the seismic data. There's discoveries, and that's what explorers do. They discover. Yeah. So I'm an explorer. So I'm not an astronaut. I never have been.
Fair enough.
I'll probably get motion sickness getting in and out of this chair. So unfortunately, I work with astronauts. I play music with astronauts. Super fun. They're in our unit sometimes. And so it's really pretty awesome to interact with these people. But I'm not an astronaut, but I'm an explorer, and we're all kind of explorers. I think we have like this thing that happens in our culture where we don't necessarily own the fact that we're born curious, therefore we're born explorers, and then life happens and we stop owning that we're all equally curious and we're all equally explorers.
You said something to me that really, really resonated with me on just, you said, I'm just a learner. I'm just a student. The data is the teacher. And that you can apply that to so many places in your life where it's, if you're, have your eyes open, you're willing to take in information and learn from your environment and your experiences and everything like that. That was really powerful to me, because on an academic level, the data's the data, it's spreadsheets. But I almost put that kind of on its head and like, oh man, it's kind of life.
It is. It is. And it's a good, I'm glad you reminded me of that, because to the rest of your question, do we have devices on the moon? There are devices on the moon, and we want more.
Interesting.
The Apollo left seismometers on the moon, and those were running for a good 8-ish years or something. And we use those data to study the inside of the moon. And we have a paper on the moon having a core. And you need data, right? Otherwise, it's a theoretical exposition of, does Venus have a core? Well, let's see. What's its size? What's its shape? And similarity to Earth. And so we could do a theoretical, kind of investigation. Right. And we can argue about it at meetings and in our papers. But
the data,
you need the data,
is what teaches you what it actually is.
Right. And if I ever start claiming I really know something, about the planet, if you can't get there and touch it and see it and measure it yourself, then I'm suffering from the plight of the human mind to start to think I know something, and I'm putting myself in this position of I know. Then I stop seeing.
Right.
And that's the thing about data. And I was super fortunate with my PhD supervisor. He was the most curious person. He would see, we'd be walking to lunch and he'd see a bird and he would just stop and look at it. And he'd ask a question and make some statement. And I would just be like, wow, this guy's amazing. So he was always taking in information and and not saying he knew anything, And so looking at seismic data, it's not only a teacher, that to remind me to not like think I know something, but it, I guess it tells us about the Earth if we try to study it, and then what scientists do is try to reproduce it, make predictions, do the data agree? But it's a life lesson, right? So yeah, if I hold this base up and I drop it, I know gravity's gonna pull it to the Earth, right? Because that's knowledge,
Right.
Because we've had enough experience doing that. But saying something about something we don't observe, like, can you predict the next time I'm gonna get furious and yell at someone?
I could say something so you are.
You could try, and it may or may not trigger me. But if we had 5 decades of being exposed to it, you might know. You might have more data, but you still might not predict it.
Yeah.
So, is that earthquake going to happen in Los Angeles or San Francisco? Do we have enough data to know? Do we know enough about the Earth? Do we know enough about how stress is stored in faults, whether the tectonic plates are still moving and stuck there? There's so much we don't know.
Right.
So data is kind of like, data's it.
It's the teacher.
I love it. You so you got your PhD in Caltech, geophysics, and what did that look like for you? Why geophysics? What no pun intended, but what resonated with you in that field?
I never knew what I was going to do when I grew up. I thought I was going to do construction with my brothers until I met some guys in a bar who were going to take algebra at the community college. So I did with them.
Huh, okay.
And then we just started taking all the science classes, and then we ran out of science classes after about 3 years. And so they were like, well, maybe what do we do next? I don't know. Someone said that's when you apply to go to a different school, go to college, I guess. And so I went and became an undergraduate. And then when I finished in geophysics at Berkeley, I didn't know what I was going to do. And one of the professors was like, well, you could go work for an oil company or go to grad school. I didn't really want to work for an oil company at the time. So I was like, I'll go to grad school. So every step along the way, so at Caltech, when I finished, I didn't know what I wanted to do. And someone said, well, apply for this postdoctoral fellowship. And then someone said, apply for this position at Berkeley. Oh, then apply for this position at Arizona State. And so here I am it was never like, you're going to be a geophysicist.
Right.
Doo-doo! The sky opens up and I see geophysics. And I didn't know what Caltech was even. I was like, there's Cal Poly in California, there's Caltech. And just one professor who is super influential for me as an undergraduate, just gave me 5 schools I should apply to. I applied to all of them. And I went and visited all of them, and the students at Caltech seemed happy and curious.
So with your style of teaching, like, what speaks to students? What are you doing differently? You would think compared.
There's the curious side of me that doesn't know and would like to know, because I goof around a little bit.
Sure.
Where I even play music and have jam sessions in the class. We have a lot of fun and demos in the like the 100 level courses, the geology course. I try to make it relevant to the students. So I don't know how much that works in terms of them retaining things, as opposed to like, hey, I love this class. Today he blew up a blah, blah, experiments going wrong and that kind of stuff. Super fun. But in the more graduate courses, I still try to keep it real.
Right.
But I don't really know when I'm getting over and not getting over. It's not that I have imposter syndrome, but I always feel that there are great teachers where you're like, oh my God, they're so eloquent. I'm kind of not that guy. I'm the crazy professor who did something, that they were just talking about. And oh my God, did the police really come in and arrest a student? Or,
Well, and we've had a few professors on, and imposter syndrome has come up just about every single time.
It's a very common thing at a very high level, which surprised me.
Have students who like some of the crazy things I do in the 100 level instruction classes where I goof around a lot, play music, do experiments. And then in some of the upper division classes, I try to make it meaningful. So in geology, like the 200 student introduction to geology class. Like when I first got here, I'd never had the course because my degrees are in geophysics. And so I didn't know anything about intro geology. So I was just reading the book like weeks before them and just trying to regurgitate content. So there was no magic to it at all. I was pretty insecure about kind of talk about, like imposter syndrome and being a charlatan. That was me. But as I grew up kind of through the years, to learn the stuff enough to like, well, this is actually really cool. Like now my perspective is it's nature. Yeah. Like all of nature, you could look at it through the lens of what we might call geology, because it's all processes, it's all environment. And geology is about like, okay, the rock record and how that relates to environment and evolution, all of these things, dynamical processes, earthquakes, volcanoes, you name it. But it's happening right now all the time, all around us. So I'm like, what an amazing class to try to trigger curiosity in individuals. Can we learn how to observe differently? Can I play a role in people rekindling curiosity to the world around them? So that's my take now. I don't care if you memorize rock names or processes, but can you look at the world around you like with curiosity? So I'm super into it now because that's like a journey for me. I don't know how to do that, but that's my goal.
You talked about exploration. You're an explorer. You're always learning. You're curious about things, right? That's a very good example of like, we should all be that way, right? None of us should. The moment that we think that we have it all is the moment that we stop learning, right? And that's a problem. You own Garnero Guitars. I have to imagine that what led to that is some of that exploration, some of that curiosity, some of that wanting to know something you don't already know or to learn something. So how did we go from the earth to guitars and bass guitars in particular?
I wish I knew that answer. No, it was a slow motion, like viscous fluid, the syrup slowly moving off the pancake. And then now I'm making guitars. I play bass and I was playing in bands. And in Phoenix, we're super lucky to have the Roberto Venn School of Lutherie. And I was super fortunate to know one of the instructors there. And so I was taking my bassist to John Reuter regularly. And we played at the same bar that no longer exists in Tempe, the Sail Inn, this classic old place.
I played one of the last shows there that they had before they closed.
And so I think he was getting tired of me bringing my instrument. He was like, you can do this. He's like, buy this book written by this famous Luthier. So I bought the book. He's like, start doing this yourself. Like, okay. And so he was so forceful and was like, you could do this. You should start doing it. That I actually started fixing my basses a little bit. And then I got the nerve to repair a guitar body where I just shaved off the top 1/4 inch and glued another piece of wood to it. And I thought, oh, that's cute. And then I started making channels inside the bodies, gluing wood to it. But I'd never make a guitar neck because only real luthiers do that. I'm not going anywhere near neck. And then I was like, well, why don't I try? But then I would never make the fretboard, right? I made the neck, but not the fretboard because only real people make fretboards. And then I'm like, well, maybe I'll make a fretboard. So it was like one thing after the other. And there was so much fear in this, I don't do this, so I can't do this. Like these making the instruments has also been an amazing journey to like realize that, wow, anybody could do anything, right?
Yeah. Right.
Like I can make instruments now. It's like a recipe. It's actually not that hard. It just like you could become a great cook or an auto mechanic or cross stitch or whatever. You just have to do it. So now I do it. And I just built a shop in my backyard to try to get better. And so I'm establishing a new workflow to make more instruments because I have like a 2-year waiting list, which I'm like, what? How did that happen? And so
didn't want customer service.
I know.
2-year wait.
2-year wait list.
Yeah. Now I'm convinced that this world of ours is so interesting and there's such division in our culture that I'm compelled to make instruments because when people make music, something beautiful happens. And the division is replaced by art and beautiful self-expression and harmony. And if I can make an instrument that someone is compelled to make beautiful music, then it's a win. And so I'm just like, okay, I'm going to do that. I was talking to a climber about gear, and that when you just start out, you may not know the difference between a $200 piece of gear for some sort of thing and then a $2,000 piece of gear for something until your muscles and your body and your awareness grows around the craft. And so I would say if someone's starting out on a bass, go get a $200 bass and stop by my shop, and we're going to set it up to be the most easily playable for you, and get a good amp, and you're going to have massive fun.
Right.
And if in a year you're like still playing, then go to that next level. There are so many amazing makers, especially here in the Phoenix Valley, because we have this guitar making school. There are dozens and dozens and dozens of makers who are trying to find people to buy their instruments.
This isn't just your average bass. There's a lot going on inside of these. And I think you are innovating on a proven model, the bass. So for anyone who's listening who isn't familiar, this is a bass guitar. Most of them are 4-string, but basically they hold down the fundamental in music. So you'll typically see, I don't know, a 3-piece, drummer, guitar, bass. But what Ed is doing is wildly different from what's been being done for decades and decades. And from our conversations on it, you are applying a lot of the science wisdom that you've gathered over the years studying wave propagation and resonance and all this, and you are putting it into the instrument itself.
That's very generous, the way you describe that. It sounds like E equals MC squared or something, but
well, so on the inside of these instruments, right? These aren't just solid bodies,
correct? Which
typically they are. They could normally be alder 2 or 3 pieces that are glued like this.
Yeah.
But yours, and we actually have a couple different sections and samples, but they're chambered.
Yeah.
And they're chambered. You're developing and working on, not to spill the beans, but you're working and developing on chambering them so that the fundamentals of the notes reflect the actual insides of the instrument, right?
Yeah. So I need to hire you to whenever anyone's asking me what I'm doing, because that was it really was more generous, because I have not thrown all the tools of my day job at these instruments in terms of some of the things that you guys can do here, which I'm excited about. That there are channels inside this thing, which my hope is when you play a string, which you can't quite hear unless it's plugged in, but
yeah.
Are you hearing it?
Yep.
Oh, cool. So that E string is vibrating. In a normal solid body instrument, that energy goes into the wood and it starts to attenuate and be absorbed. And there's a magnetic pickup under here. So when a metal thing is moving over a magnet that is wrapped in a copper wire, it makes voltage, and that goes out of the instrument to a speaker. So an amplifier that takes that. So why let all of that vibration die in the instrument? So my philosophy is, if we put channels, and a lot of people do chambering,
right?
But they'll drill holes, little peanut-shaped holes, or big chambering. Some of my early resonance ideas were just big old channels. What if we make them so that they're certain lengths, such that certain pitches can light up, if you will, almost like tapping the wooden box with a different little.
That was going to be my next question.
Right. So that the body vibrates more, so the string energy, that energy then goes back into the string. Because if the body's vibrating, that feeds into the string. Yeah. Just like when you're probably hearing the strings from me tapping the body. So that's, depending on where I tap, it might highlight different overtones being, and so you can get different pitches from the same string. So depending on where you tap it, you might light those up. Why don't we do something that sympathetically allows those vibrations to keep going, so that the instrument now, because all that matters is what is going through this wire, right?
Right.
So it has to happen above the pickup. So let's give the string some of that energy back by bringing the body to life. And so I have, can I bring these up?
Yeah,
Of course.
My props. It's a shark. So this is on the inside of these things. I don't know if the camera can see that or not, but and this is slightly different design than what's inside there. But so these channels, my newer versions are getting a little more systematic about the lengths of these, and this is maple, so it's a hard wood, so it doesn't absorb as much. Anyway, so there's a sound pitch from things that are that you hit the string, it vibrates the body, and my hope is these things come to life, and that keeps that body vibration, then goes into this thing we call the bridge that the strings are rooted in, and the pickup can sense that energy because the strings are not dying down or attenuating, per se. So that's the goal.
Now, you're hoping to shape these cavities to be sympathetic to the instrument itself and the notes that they're tuned to.
Yeah.
So at this point, you're experimenting with widths and lengths and of the chambering.
Yes. And so my newest versions, which are just on paper, they're not printed yet, especially for guitars. And I think the guitars, because the overtone pitches that are specific to those channels are very high on the instrument. They're higher than the highest note on this instrument, which is, this is a G. Maybe they're in the 5 notes and above that. So they're in the overtone range, so the crispness of the sound of the strings, which is very high frequency, the overtones of those harmonics that I played, it's in that range. But on a guitar, there's more of a range on the fingerboard that those notes can be fed to come to life. But what it does on the bass loses a ton of weight. So this is like 2 pounds heavier than most 5-string basses. You feel the vibration on your body more because the instrument does. Yeah. Put it against your body. And if you play a low note and just feel, it's just the instrument is a little more alive. So you can feel that on your body a bit.
Yeah, absolutely.
I was gonna say, just putting my hand on it, I can feel it.
Yeah. And even down the neck too, because most necks are pretty dead.
I want to, like you said, be able to tune the construction of those cavities to see how much does it work.
Right.
Yeah. Very cool.
Like this one that's an in-progress one. This thing is a 5-string bass with strings on it and electronics. It should weigh 9.5 pounds if I'm buying a Fender.
Right.
And that's a pretty good weight. It doesn't have the pickups yet. But this weighs like 5 pounds and 1 ounce. And it's super, you could tell that there's different pitches to it. So I think this guy is really going to come to life when it's strung up. But how so? Is it coming to life the way I planned?
Well, and part of what we're going to be doing, and Ed's given us permission to do that, is we're going to be conducting a bunch of tests. So after this, you'll see quite a few of those tests happening where we're testing the resonance of solid body and semi-hollow and completely hollow on an acoustic, because once again, data is the teacher. We can't thank you enough for being here. It's truly been a pleasure.
The pleasure's mine.
Thank you for coming in. We'll be sure to put up all your information for everyone to see and be able to visit your social and everything else, your TED Talk.
My 1 million publications.
Your 1 million. Yeah, just keep going. Play this a little bit.
Sure.
And then we'll go in.
Play us in, huh?
Yeah.
I've been playing 4-string for about a week because I remodeled a 4-string and it's totally goofed me up.